So hello to everyone. I'm going to talk about vibrational duetting and signal production in Aphrodes makarovi leafhoppers. Aphrodes makarovi leafhoppers are hemipterans belonging to the Cicadellidae family, and because they belong to a family with more than 20,000 species, they are relatively common, relatively big, and their sexual communication is exclusively based on reciprocal exchange of vibrational signals. They become model organisms in studies of vibrational communication and sexual selection. So just a quick overview of how their communication looks like. Males move from plant to plant where they emit advertisement calls. You can see that male call has a complex structure, and it can be divided into several structurally different sections. When there's a virgin female in range of a male call, she replies here. And you can see that female reply is very, very simple. It's just a repetition of single pulses. And you can also notice that female reply starts before the male call ends. And during female reply, male searches for her, and shortly afterwards as well. Males emit another type of vibrational signals. It's so-called masking signal, and they use those signals in rivalry situations to overlap female replies. And as you can see, masking signal is just like a female reply, very simple, it's just a repetition of single pulses. So, Aphrodes makarovi leafhoppers face many challenges to find their mate. First of all, they need to deal with physical properties of the plant. Their signals has to spread around, and their receptive system has to be able to perceive vibrations from the very, very noisy environment. And not only their potential partner is able to receive their signals, there are also predators, parasitoids, and rivals around, and everyone is waiting for their chance. And you can imagine that advertising yourself in such a complex environment requires a lot of energy, and it's also dangerous. And to reduce their costs, males often switch their behavior and use alternative behavioral tactics. So, how do Aphrodes makarovi leafhoppers produce their vibrational signals? In 1949, Åse Nilsson described in Aphrodes bezinctus, in the first abdominal segment, striated tymbal with 9 mediolateral furrows in females and a convex integument in males. And when we checked Aphrodes makarovi under the scanning electron microscope, we see exactly the same as Åse Nilsson saw. So, convex integument in males and a striated tymbal in females. Of course, we wanted to check what is beneath the tymbal. That's why we used micro-CT to see what is below. And the black arrow indicates the tymbal area. And you will see that just below the tymbal, there's a huge dorsoventral muscle, and Åse Nilsson named it dorsoventral muscle 1 from the first abdominal segment. You can see that this muscle is especially huge in males, and you can see that there are some other muscles around. Some of them are attaching very, very close to tymbal. However, their function is not yet known. And of course, we wanted to see how this DVM muscle works. That's why we inserted measuring electrodes, as you can see here, and also a reference electrode. And at the same time, we were recording signals with a laser vibrometer, and we recorded the movements of the tymbal with a high-speed camera. And what we got, you can see here from the EMGs, that left and right DVM1 contract at the same time, and that also means that both of the tymbals buckles at the same time, and this means one pulse in the signal. We recorded signal on the ground approximately 8 milliseconds after the beginning of the EMG, and this might be due to the latency of the muscle and because of the transfer to the ground. Of course, we wanted to investigate DVM1 a bit more. For that reason, we used transmission electron microscopy, and we saw that DVM muscle contains a lot of myofibrils, very thick, and they are very especially thick in males compared to the females. And those myofibrils comprise of approximately 50% of the muscle volume. There are also numerous tracheolae and plenty of mitochondria with a very, very dense matrix and many cristae. And this total mitochondrial area is much bigger in males compared to the females. And there's also a lot of smooth endoplasmic reticulum, and all this suggests that DVM muscle is a fast muscle, and as such it requires a lot of energy. So of course we were trying to assess this energy input, and respiration rate correlates with energy consumption, so we measured it, and respiration rate in males was 2 times higher at signaling than at moving, and 10 times higher at signaling than at rest. When we compared males and females, signaling respiration rate was 1.5 times higher in males, while during resting, respiration rate was 1.4 times higher in females. But what does this actually mean to them? Our experiment showed that higher signaling activity leads to a shorter lifespan, both in males and in females. And not surprisingly, duet is really precisely coordinated. And we know from our previous experiments that females never emit their signals on their own. There has to be a male call. And we also noticed that male's advertisement call is changing with age. So we wanted to know whether mature females always reply to a male call. With NMDS analysis, we were able to show that there's a group of young males that really stands out. And you can see from the graph on the left that females were generally replying to younger males less often compared to the others. However, behavioral experiments with natural trios showed that females were replying to both males in the experiment equally, but those males are of approximately the same age. But what was interesting is that no matter whether a male actually mated with a female in the end or no, the females were replying to both equally. So without a female reply, males just cannot locate females. And in one of our playback experiments, we showed that, if you remember from my previous slides, I pointed out that female reply starts before the male call ends. And we were interested whether males are also able to detect the female reply, which is inside the male call. So we tested that, and that's here in blue. The female reply was so short that it was actually hidden in male call, and you can see that male's behavior was similar to the situation when there was no female at all. And when the female reply was just long enough to be visible that males can actually detect it, the male's behavior was very, very much different. So, as we saw before, very, very short replies as well as very long replies cause problems to searching males, as we can see from the comparison with an average situation, which is here in black on the graph. And what was also very interesting is that males started emitting masking signals over long female replies. But what really stands out is that only at average female replies, cumulative signaling duration for males and females were equal. So at short female replies, cumulative signaling duration was much greater for males, and at long replies, cumulative duration was greater for the females. Another very interesting thing from our experiments with natural trios, where we had 2 live males and a female, is that whenever it was possible, males switched to alternative behavioral tactics. They started emitting masking signals. With them, they were hiding female replies for the rival male, and they started exploiting duetting male. So when male was in a duet with a female, the other male was just listening and following the female reply and actually they were very, very successful in doing so. And as you can see, there were some males that didn't need to emit any call at all, and females accepted them and mated with them. And in general, the males that mated with the female were heavier, which maybe indicates that they were in a better physical condition. So maybe females use also this as a kind of how they evaluate the quality of the male, not just by the signals. So as you can see, there's a lot going on among males and female leafhoppers, and it's really, really interesting and also quite complex, as you can see. So thank you very much for your attention, and I would also like to thank to everyone that contributed to my research.